Welcome everyone to today's webinar on 3D printing. I'm very happy and excited to have you all here. I'm your moderator for today. My name is Anjali and I'm a marketing manager at Fraunhofer IPMS. And with me today we have Severin, who's also from Fraunhofer IPMS, and Jochen, who is from Nanoscribe, and together we'd like to present this webinar to you. If you have any questions, please use the questions form that you have in your chat, or just send a text and chat message to me if there's any issues that you're experiencing from the technical side, maybe. And all questions will be answered at the end of the webinar, so I will be moderating them and then asking Severin and Jochen all of your questions. And without further ado, I think we can start. So Jochen, I'll hand over the slides to you and enjoy the webinar, everyone.
Thank you very much. Welcome everyone, also from my side. I trust everybody can see my screen. And this is my intro slide. So my name is Jochen Zimmer. I represent the company Nanoscribe, and we are partnering here. So we're happy and thankful for IPMS to organize this nice webinar. Just have one slide about Nanoscribe in general. So we were a spin-off almost 16 years ago from the Karlsruhe Institute of Technology. We're not a spin-off anymore. We have over 100 employees at this point, most of them still working in the region of Karlsruhe, where we have the R&D, production, administration, and everything. We have two small subsidiaries and offices in Boston and Shanghai to have sales and service representative in the regions. Most of our over 4,000 registered users are in the field of academic research. So there's a big pile of peer-reviewed publications at this point, but we do have a growing number of industrial customers as well. So let's get into the first part. This is a short introduction on 3D printing, a few slides in general, but then mostly 3D printing with two-photon polymerization. 3D printing is quite an old idea. The first reference that I could find is actually from the 19th century. And I like to have this in my slides just to introduce the basics to you. So the idea in this patent was, if you want to have a physical representation of a geographic height map, you can just take the height map with the different lines of constant height and cut a piece of wax or wood or whatever along those lines. And then when you stack them in the right order, you can get a physical representation of those heights, of those mountains and valleys or whatever. And this is the basic that is behind most 3D printing up to this day. You discretize, and then layer by layer you manufacture your object. Of course, since the rise of automation, this is no longer done manually, but instead by machines. And a common 3D printing technique is called stereolithography that was invented and patented in the 80s. And this is very similar to our technology. So I can use this to explain some of the basics. You have a laser in both technologies, and that laser shines onto a reservoir of UV polymerizable resin. And then the laser beam is moved to the different positions in a layer. And this is used then to cross-link and polymerize the resin in specific locations. And then you move by some method in a delta Z. And in the end, you have a polymer object that is basically built out of the cross-linked resin. And this is the same in both technologies, stereolithography and two-photon polymerization. But let's dive into the two-photon polymerization part. So also here we have a laser source. The laser beam is moved around by galvo mirrors in this case, and it is focused through a microscope objective into a reservoir, which is mostly just a big drop of UV resin. And then again, you scan layer by layer and you cross-link the UV resin locally. Naively, you would think, you would also use a UV laser, and then each individual photon would have enough energy to start a cross-linking reaction, exciting a photoinitiator, and then you could locally polymerize. However, this does not give you the right confinement, especially in the Z direction. You do not get a good confinement here, so you would have a larger region of this double cone, basically cross-linking in every position. and this is not a good way to do microprinting. So instead, we use a femtosecond near-infrared laser. So now the individual photons don't have nearly enough energy, so they just fly through the resin without any interaction, basically. But if you get close to the focal point, you can get to a regime where you have enough energy so that two photons can be absorbed at the same time, starting a cross-linking reaction here, but not elsewhere. And this is why it's called two-photon polymerization, and it gives us a very high degree of confinement. We can go to sub-micron line widths easily in all three directions. This is used, like I said, we're 16 years old almost, so this is used by many of our customers to build all different kinds of nano and micro parts. One example, just as a brief introduction, is here this multi-lens objective that is less than a millimeter high and much less than a millimeter wide. And as you can see, this can be printed in high quality and in high complexity. So this allows you an unprecedented degree of integration and miniaturization without getting to hundreds of process steps. This is done, in this case, on a Photonic Professional GT system, which is also the type of system that our host, Fraunhofer IPMS, has in their lab. And this is a very versatile microprinting tool. It is actually the third generation after Photonic Professional and Photonic Professional GT. This is now the GT2, the third generation. And this is used by hundreds of customers worldwide. I just have two short examples as an introduction before I hand over to Severin for the Fraunhofer part. So one example here is, again, the multi-lenses, and this is actually one of the people behind the previous design as well. The company that they formed out of this was called Print Optics. So this is a multi-lens objective printed directly onto a microelectronic part. So this is a multiple pixel detector. Actually, it's a webcam chip. And now you can directly focus the light and read out the individual pixels by printing directly onto this chip. And not only can you print onto a blank chip like this, but actually you can also print on more complex shapes. So this is now an example from the world of microfluidics. And here you have some channels that were pre-existing. You can also print channels, but let's say these were made by a different technology. But then you can put some resin inside here and print into the channel. So actually, because the last solid surface is the objective, and then you have a little bit of working distance, you can actually print into gaps and channels and onto the side of things, which makes this a very versatile tool for multi-approach manufacturing. And in this case here, the customers printed this 3D microfluidic part into the channel in order to combine the flow from this and from this channel into a third channel. And the content of this channel is actually injected through this tiny nozzle into the stream from the other channel. And this is used to make a very thin thread of material, which is built when the two materials come in contact in a very controlled manner in this microfluidic chip. And if you just fill it with painted water, just to visualize the process, you can see here that this actually works. And with this, I come to the end of the introductory part, and we'll see each other later. And for now, I hand over to Severin. Thank you so far.
Thank you, Jochen. I'm trying to share my screen right now, but I think I have to wait for the moderator. Just a second.
It should work now, Severin. Is it working?
Yeah.
Yes. Okay.
I guess. All right. So welcome to my second part of the Aligned 3D Printing webinar today. And thank you, Jochen, for the introduction to the basics of 3D printing and two-photon polymerization lithography. So my part is concerning the work that is being done using the systems of Nanoscribe and other systems here in Cottbus. So let me show you the locations of Fraunhofer IPMS. We have the main location in Dresden and a second location in Dresden as well, and then 2 locations outside Dresden, where we are here in Cottbus with our specific lab for 3D printing. And inside the lab, we have our clean room and our, as Jochen already said, our Photonic Professional GT2. The system has some specifications. If you're interested, of course, we can talk about that, but I would go over the main features that we can do that maybe nobody else can do. So during my PhD that I finished this year, I was able to do an upgrade to the system to allow substrate alignment for chips and assemblies, MEMS. And we also have some fluid dispensing and microassembly available, as well as a really well stacked optical characterization suite. So all of these are available, and now I want to show what we actually do with these systems and how I want to go through here step by step through the scale I put here on the left. So starting with very small objects, going to very or kind of large objects in our realm at least. So starting in the low range, we have one of my experiments, an optothermal experiment. These lines are very small. The idea was here to find the substrate effect. So depending on the substrate, we can receive an effect on this printed line across these 2 holders here. And depending on the distance to the substrate, actually, we can receive different amounts of effects. On the right here, we have some acceptance testing nanorods. These are usually printed to show off what the system is capable of after installing. And we are actually working with the 100 nanometers here. Of course, you could go a little bit smaller even, but that depends very much on your on the structures that you're actually designing. Going one step up, 1 micron, here we have one more of my PhD works. This is actually a chip, an ultrasonic chip that received a structure on top of it. So the round structure here is printed, and we can see a few micro channels here. This is basically an acoustic experiment, and the idea is just to show off what the system is capable of here, of course. And on the right, hexagonal microchannels. This was also part of the acceptance testing. You can see the structures. If we go up to 10 microns, we have a C60 model. This is a very standard model to show off that 3D printing allows hollow structures, overhangs, and so on. Then something we recently are doing is printing microlenses, and especially microlenses made from PDMS. There's a new material by Nanoscribe. They offer the IP PDMS, and this is useful in some applications. So just to show off what we can do here with this material. And then one of our publications shows off topology optimization. I wanted to put it in here as well. This is a grating, an acoustic meta grating, and this is used for deflecting an acoustic beam. And here we have the quite random looking topology optimized structures. And this is one of the benefits of additive manufacturing in general. You can just let the system design something for you and then fabricate it. And if we go one step up in the 100 micrometer range, this is the grating from the side view again. The distance between these, the pitch here is about 300 microns, and you see it in a sample frame, and this is to allow the user to hold it and then place it across the acoustic path. On the right, we have one of our parameter sweeps. I guess everybody knows what that is. If you've ever done any 3D printing, you just change parameters depending on this location for an identical structure, and you look into the structures to find out what the parameters actually do to it. And what we did was Raman spectroscopy and nanoindentation investigations. And this was to find out polymerization, the polymerization degree. So this is a more complicated. So maybe if there's questions, I can go into it. If we go one more step to 1 millimeter, we have the microneedles seen here. This is for one of our customers, which is doing nano imprint lithography. And basically, we printed the needles for them to use as a master for the molding type nano imprint lithography. So they punch the needles into another material, and then they can infill with the target material. On the right, we have another piece of the acoustic grating. So this is a holding system for the slide. So this slide here, the sample frame, this slides into the top part here so that it locates the grating towards the chip. And this is hollow inside as well to save some volume, and quite large for what we usually do. Usually the idea is going smaller, but sometimes we print some big stuff. So at our location, so this is the building I'm in right now, and with the lab, we are located in Cottbus, near to the library. And the library is a landmark everybody knows once you've seen it. And we printed that using the system as well, just to show off the capabilities in 5 millimeters height. So you can actually see it with your eyes, which is good for showing off the functions. And yes, quite detailed, hollow inside as well, and still took about a weekend to print this. And now I want to go into a little bit more the fabrication on chip. So for that, I want to go into the applications that are for which this printing method is useful. So fabrication on chip, there's a few application fields coming from Fraunhofer IPMS, smart industrial solutions, quality of life solutions, and we also have the medical and health. So here we have the application field, which also works with acoustic sensors. And one of the acoustic sensors is in this otoscope, which is an acoustic detection system for infections in the inner ear. And wouldn't it be nice to improve this by printing something on it? And first of all, we have to put the chip inside the system. And if there's roughness or wafer bow, for example, a substrate can be tilted towards the optical path. And if you print on it, you will result in either structures being inside the substrates, partially being disconnected, or just completely disconnected. So to fix that, I improved the system by giving it an upgrade, tilt compensation upgrade. Here we have the look inside the system from the top, and we're looking inside the optical path here. And usually we have three axes available by galvo scanner or by piezo stage. And with the additional upgrade, this is the system here, we can actually have 3 additional axes, and the rotational axis, and the residual tilt for what I found out was that we can go down to very low degrees of tilt, 0.04 degrees actually, and this was making it possible to print something on one of our acoustic chips. So the acoustic chip here, the CMOT capacitive micromachined ultrasonic transducer, it's located on one of our chip holders, basically a packaging system. And on top of that, printed in green here, this is the acoustic waveguide. So in the center of the chip, there is an aperture that produces sound, and then this guide improves the directivity and the acoustic matching to the surrounding air. In the image here, you see this TO18, so this is the housing for the chip. It's glued on top of it, and then we have a coating around the chip. That's why you don't see it. And inside the coating as well is the horn, the waveguide here. Yes. So to sum up, we can fabricate from sub-micrometer to centimeter, which is great. You can do a lot of prototyping, and we have a very fine resolution with the system. And we can go on chip and on PCBs even if you want to. And we also allow microassemblies. We have some, fineplacers and the necessary equipment to do microassembly here. And potential applications, we already talked about a few of them today. Acoustic and electromagnetic metamaterials are interesting. And we're also going into optical microcomponents and the masters for nano-imprint lithography. You've seen it. The idea now for us for this webinar is to find your problems, the problems of our customers, and maybe create something based on those problems, make some ideas happen. Yes. All right. If you have questions at the end of the webinar, I'm happy to answer them. Otherwise, contact me anytime. I'm always available. So yeah, next is Jochen again with his second part. Let me end the sharing here.
Okay, thank you. I hope I'm back with my shared screen and my voice. So let me pick up again. And now we're entering the third part where I'm going to talk a little bit about our next generation of microfabrication technology, which is implemented in the Quantum X systems. And very recently we launched a new platform which is called the Quantum X product line, and it has different varieties. For example, Quantum X Align, which I'm going to mention later on in the presentation. And so opposed to the Photonic Professional GT2, which is a very generalized multi-purpose system, these Quantum X come in different flavors that are more specifically equipped for some specific excuse me, some specific applications. So in part 3A, I'm going to talk about tilt compensation on wafer scale. And before I can do that, I want to very briefly introduce a new cool variant of two-photon polymerization that we invented for this application. And for this, let's briefly look at the effects of the discretization. So I mentioned in the introduction that 3D printing always, or almost always, discretizes a structure that you want to print in a layer by layer method. And this works well, and you somehow have to discretize it if you want to build it layer by layer. But for some examples, specifically the optics that we now mentioned several times, this gives you the challenge of having a surface quality that is not really suitable for optics. And there could also be other like medical, biological, fluid dynamic applications where those surface roughness introductions could not be ideal. And you can overcome this by reducing the slice thickness, making it thinner and thinner, and at some point the steps basically wash out and you will end up with a very smooth surface. and this works great. And we have seen very successful customer applications implemented with this, but it always takes a lot of printing time. So there's this fundamental trade-off between you can go fast, but then you have a very rough surface with lots of discretization artifacts, or you can go slow, but then you can have a smooth surface. This fundamental trade-off we somehow wanted to get around. And this is why we invented two-photon grayscale lithography. So we're briefly going back to the sketch of how the technology works. So again, we have the galvo mirrors, the microscope objective, and the light is focused into the UV resin droplet. And I mentioned that there's a certain region in which we go above the two-photon threshold and certain regions where we don't cross it. So there's a region where we get two-photon polymerization and everywhere outside we don't. You can visualize this by plotting schematically the laser intensity. Actually, you have to plot laser intensity squared because it's a nonlinear process. We're actually dependent on the intensity squared. But either way, at some point, this will be above the threshold, and some other point, it will be below the threshold. Again, just one direction picked out of random here. If we now change the laser power, you can easily imagine that the line becomes smaller in all three directions. So now by changing the laser power, we can change the total size of the voxel. This is also possible on Photonic Professional GT2. However, if you want to use this dynamically, you have to make sure, and this is something that we just learned afterwards, so this is now implemented in Quantum X, is unfortunately not possible to retrofit. So now if you synchronize the galvo movement and make sure that you have real-time control of your voxel in the megahertz scale, you can actually get around this fundamental trade-off that I mentioned earlier. So instead of going layer by layer and just switching the laser on or off at a specific power, you can now actually dynamically change the laser power in order to change the height of the layer while you are printing the layer. So as you can see here in this sketch, but this is actually quite accurate, you can reduce the number of layers and still end up with a much smoother surface than you could previously. So this is called two-photon grayscale lithography because it has the power change in order to change the structure height in common with conventional grayscale, although as you could see, the details are quite different. But this is going to be important in a moment. This is implemented in the Quantum X line of products. So this was already hinted at before in the talk by Severin, but I want to show this a little more detailed here because it's very relevant to how we implemented it. If you do 2D lithography, you basically just, the laser beam is almost parallel, and you illuminate your material, and usually you can penetrate all the way in. And whereas in our case, we are printing layer by layer and we have a very tight Z confinement. If we now work with a slightly tilted substrate, as unfortunately is hard to avoid, even if you build all the parts, but especially if you have like customer specific holders or anything in it, it's very hard to get to this precision that we saw before. 0.0 something degrees is very hard to achieve mechanically. This can then, in this case, lead, as you can see here, either to sinking in the substrate or not being properly in contact with the substrate. This is bad enough on a single structure, but if you want to make something that's larger than a single print field, then you run into even more trouble. So in this case, you can clearly see if you just measure the height once and you print at the same height everywhere, then at some region you will lose most of your structure, whereas in the other region you will have a complete delamination. And this is a mechanical problem waiting to happen. This will eventually just get disconnected from the substrate, and then you don't have a printed structure anymore. Typically, there's two ways to avoid this. Either you basically measure the correct height in each field individually, and then you can have a structure that is well connected everywhere and has roughly all the features represented, but you will get these steps at the stitching seams, which can be problematic for optical, mechanical, all kinds of applications. Or you make a thick socket below it, and then it's okay, you don't get delamination, but you lose lots and lots of volume that you put down basically in vain, and still the structure is actually not parallel to the substrate surface. So this is also quite far away from being a perfect solution. We implemented this a little differently. Mechanical would have been an option, and we've just seen that this can offer some great results. We went down a different path. Still, of course, you have to measure your tilt. In our case, we do this by doing a multiple spot interface find. So now we know for the individual print field whether or not we have a tilt and how big the tilt is. And now we just rotate the whole design before slicing it. So the slicing doesn't happen before the print, but actually during the print, and it happens in accordance with the correct tilt to the structure. So if you would do this with a conventional 3D printing approach, you could again achieve a good adhesion everywhere, but you would again get some discretization errors for a finite slicing height. So again, you would have some kind of steps in these features, and those steps would be in different positions depending. So, so this would also be quite far from a perfect solution. But if you combine this tilt correction, rotation, and then you combine this with two-photon grayscale, you can actually get a smooth representation of the original surface, perfectly parallel to the underlying substrate, and you basically get the best of both worlds, and you get a correct representation of your structure, even with a slightly tilted surface. And we have tested this and implemented this for the customers. And here you can just see one example. This is a multi-lens array with concave and convex lenses of different sizes. So this prohibits us from hiding the stitching just between the lenses, as is sometimes done. So in this case, there's unavoidably some lenses will have stitching seams, and you can clearly see them here in the picture. Now with the same machine, the same design, the same scaling, everything the same, the only difference is we switched on the tilt corrected 2GL stitching. And you can see here, and this was stitched in the same position, but the stitching seams are completely invisible, and they're also invisible in the basically in the picture. This is projecting a homogenized beam, and the quality of the homogenized beam is notably improved because of this tilt corrected stitching approach. And so this approach to GL and the tilt correction is used by plenty of our customers for the nano imprint lithography that IPMS also offers you when you want to print one master of a relatively large area and then go into a replication process. So this could be used to improve microneedles, micro lens arrays, anything that you would replicate, or you could correct the tilt mechanically, as we have just seen IPMS is capable of doing now. So in the last part, part 3b, I want to talk about printing on chips and how you can correct the position and rotation and tilt and everything on complex substrates with quantum X as well. In this situation, we often encounter photonic chips. So this is the example that I'm going to go with. So what we have here is a waveguide and then some alignment markers, typically from the lithography processes that made the waveguide. And then here's the chip surface, and this is the chip side. And the goal is to couple light in or out here much more efficiently than just with a blank waveguide. And for this, you need to measure very precisely the position and the angle, because otherwise, if you print in here a lens and it's a few degrees off, then the beam will point in the wrong direction. This won't work anymore. So we have implemented this in the Quantum X Align, and we call it aligned two-photon lithography. And the sketch of the functionality here is basically the same, except for this addition here. So what we're doing now is we're using the laser, the galvo mirrors, the focusing optics and everything. We use it to scan the surface at an intensity that's below the polymerization threshold. And we're looking at the light that gets back scattered and then enters this confocal module detector. And this allows us to scan the surface in the exact same coordinate system as we're using for the lithography. So there's no coordinate system mismatch that could enter here. And we use this to detect three, for example, but this would be the optimal number, three markers, three features that are on the surface of the chip or anywhere on or near to the chip. And then if you have three positions in X, Y, and Z, because the confocal can also detect the correct height, now we can, with the 3 points, we can get the perfect alignment, position, and rotation and tilt. We can correct all that. So now, similar as previously, we are now rotating the design accordingly and printing in the right position with the right tilt, a lens that is matching, in this case, a lens, but it could be anything, of course. As an application example, I've chosen something from a publicly funded project that we participated in. So in this case, we had a chip that had multiple waveguides to get the light out. And the goal was to print these lenses here. So this is the actual lens surface. And then there's a body that's just there to allow the light to expand before hitting the lens surface and to give mechanical stability. And we wanted to print this with the chip lying flat in the setup. This actually introduces one more challenge. If you want to print to the side of a chip like this, you will encounter a so-called shadowing effect from the chip edge. So basically, not the full beam from the objective, no, the whole cone doesn't reach the bottom of the printing structure anymore, but there's some light that gets blocked and reflected or scattered away. And this will lead to a power reduction at the focal point to a reduced dose. And as you've seen, this is a nonlinear dependence. So this will very strongly affect the power that you can deposit there. And it will very strongly reduce the quality of the structure. So in order to properly print onto the side of the chip, you need to compensate for this. And we developed this together with some partners in a project a couple of years ago. And this strategy was patented, and actually because we participated in the project, we have the right to license this. And so this is also part of the Quantum X Align package when you get this. And this allowed us to print these lenses here perfectly aligned in position and angle onto these waveguides. And we characterized this as well. So here you can see the lenses again. The blue part here shows this in this region. We just did a simulation because we couldn't measure, obviously, the light inside the polymer. So the light here starts as a very small mode confined to the waveguide, and then the beam is allowed to expand in the lens. And then as soon as it's outside of the lens, we can measure the beam shape and intensity distribution. And as you can see over here, where we overlay the simulation and the actual measurement, we are in very close agreement. So we managed to design the proper beam shape that we wanted to have. For example, in this case, collimating the beam to a specific diameter, and then the beam shape and the direction match perfectly for all these lenses. So like I mentioned, this is all implemented in the Quantum X line of products. So if you're interested in using some of these techniques, feel free to contact me afterwards. I just wanted to give a quick mention of another webinar of our own that we're organizing 2 weeks from now. If you're interested in specifically this application of photonic integration and printing on photonic chips, we have another webinar of our own with external partners from IMEC and from a spin-off company that uses our technology for photonic integration, and an internal expert from our company. And yeah, that's it. Thank you very much for your attention. And if you have any questions, I think this was mentioned in the beginning, please post them into the chat so we can answer them. Thank you.
Thank you very much, Jochen and Severin. This was quite interesting and also very impressive, your results. It was great to see. I haven't received any questions in the chat yet. But I have a question. So to everyone else, you have the time now to post your questions. So do it now while those two are still online. And I have a question for each of you. So Jochen, maybe you could quickly summarize like the top three branches that profit from your printing.
The top three branches, well, I would say traditionally just general purpose basic research. So we have academic researchers that do all different kinds of things, and they have profited from this by being able to access really the tiniest structures that could be things like cell scaffolds and tissue engineering, and that could be micromechanical structures, all different kinds of things. But the main two industrial branches were basically users of what we just discussed. So one being the mastering of structures for the replication. That could be nano imprint lithography, or you could make a metal tool from printed structures by coating them, and then go into things like micro injection molding or roll to roll replication. So that's one big industrial interest that we receive, and the other one really being the photonic integration. So I couldn't show this because of time constraints, but the Quantum X line also has a module that allows you to print on fibers and fiber arrays. So you can make lensed fiber arrays that can focus the light or make it look around the corner, or it could be like a optical lab on a fiber tip or something. So I would say basic research, mastering and replication, and photonic integration being the three big fields that we receive a lot of interest.
Okay, thank you. And of course, research being one of our topics at Fraunhofer IPMS, and Severin is also from research. Severin, if people are now very interested and want to start a project with you, can you quickly outline how that would work?
Oh, of course, yeah. They would contact me or anybody at Fraunhofer IPMS and then get directed to the responsible person. And if your project idea contains any additive manufacturing requests, then that would end up on my table. And from there, I will immediately find out if that makes sense and respond to you. And of course, if the idea is worthy and we can see something working out there, we can fabricate structures immediately. One of our customers or new, let's say, contacts is receiving test structures just to show off what we can do and the materials, and this makes it really easy to find out if this makes sense for a new customer, so they can actually get a sample immediately. We can fabricate specific samples really quickly. That is one of the advantages that we have. So we're definitely using that advantage.
Okay, so if you're interested, then get in touch with Severin. And I've now received one question, and that's for Jochen. Shay writes that it was very interesting, and we've been printing V-grooves using Nanoscribe, but could not find a hard enough material which will hold a sphere compression on it. Can you advise how to overcome this?
No, sorry, I don't understand the question right now. So you're printing V grooves out of a polymer material, but it's not strong enough. Is that correct? Can you please
Yeah,
confirm in
the
the
material is
chat?
not hard enough to hold a sphere compression on it.
Okay. Um, Well, actually, I mean, there is the possibility in principle to print in a composite material, and maybe that is already strong enough, or probably you would then go ahead and sinter it. So there is a material called GP silica that we offer together with a glass printing set, and that might allow you to print something, of course, slightly larger, and then put it in a vacuum sintering oven, and then the structure will actually be made out of pure fused silica glass. So that would have a much stronger compression than the polymer has. I guess that's the best we can offer. Otherwise, of course, you can go down the replication route and print your structure and then make a copy from that into some casting material that is stronger. That would be an alternative that I could see.
Another
Okay, Shay.
alternative would be the coating strategy, metal coatings or yeah, but depending on the structure, that is not always the best route.
Yeah, absolutely right. Coating is always an option with the material. You would have to maybe make some back of the envelope calculations if that can actually give you enough of an increase. But it is an option, especially if the surface properties aren't good enough. Yeah.
Okay, Shay, so I hope that's answered the question. If not, then feel free to get in touch with either Severin or Jochen after the webinar as well. And I haven't received any other questions, so I think you both explained really well. And if there's questions left, there's always a way to contact us afterwards. I posted in the chat 2 links where you can find more information either on our webinar series or on our 2-photon lithography at Fraunhofer IPMS. There's also a link to a virtual tour, so if you'd like to see the labs, then take the tour. And otherwise, you'll get a follow-up email detailing all the information that was given out today from GoToWebinar right after the webinar. And I hope you enjoyed it, and I hope I'll see you back for another of our Fraunhofer IPMS webinars. Thank you all for participating, and thank you, Severin and Jochen, for presenting, which was an excellent webinar. And all of you have a nice Thursday and a good weekend, and see you soon.
Thank
Bye-bye.
you. Bye bye.